here we go. So yesterday we talked a little bit about some stuff. What was that stuff? Units of electricity. All right, so what did we learn about? We have now ohms, we have volts and amps, which is current. So ohms, which is resistance, which is resistance to flow, amps, which is the current flow, and volts, which is the pressure or difference of potential. So now as we start moving forward and talking about an actual electrical circuit, let's see, I'll put a 1, oops, I like black 1. There we go. So we'll say a simple circuit. Simple circuit has to contain a couple of things. We'll put that must contain. Anybody care to guess?
Battery.
All right, batteries. We'll call it a power source. And that is our supply or source of electrons. We have, what else?
Resistor.
A resistor. Okay, resistor. A resistor or some sort of load. All right, something to use the electrons. Something to use the electrons. All right, I need something else here. Ooh, a path. All right, well, I have 4 things, but the 4th may be a little harder to figure out. Anybody guess this one? All right, that's it. Connections or conductor. A conductor, something to move the electrons, something to move them. Something to move.
Would that be the same thing as a path?
Well, it would be the same thing as a path in the order that I wrote them in. Normally I write them in a different order, but I'll let you guys kind of call it out, because otherwise I could say, well, I've got a battery, I've got a resistor, and I've got a conductor. Do I have everything I need for electricity to flow? No. I do not. So by simply just saying a power source, a resistor, and a path, all I've created is nothing. Why do I have nothing? Because there's no way for electrons to flow back around to the battery. So I have to have a path, which is made up of the conductors. Now you may see a path that looks like that, or I could do a shortcut. And it looks something like that. That is a ground symbol. So I'd have to have a ground here and a ground here. And really what a ground represents, we could pretend like this table here was actually made of metal. I could set my battery here and take the negative wire and just clamp it onto the table. Then I could take my positive wire and go to a resistor, and then on the other end of the resistor, just clamp it back to the table. And that's really how a car, an aircraft, I was going to say boat, but they're made of fiberglass, not really. So we'll say car or aircraft works. Is there's just a small wire going from the negative side of the battery right to the aircraft, which is made of aluminum, and you only run the positive wires out pretty much. All right, so we must contain all of those things. If you lose any one of those, I'll tell you what we could do. We could change our load. And we'll change it to, what is that? Light bulb. All right, so that light bulb would be on, but if I do that, the light bulb is off. So I could add in a switch. There's a switch right there. So that light bulb's off. Put it down, it's on. While we're talking about this, what is this called? If I have an error right here, what is this called? An error. That's an open. That's an open. What is this error? Error. That's a short. Shark. Why did I write shark? I don't know. It's a shark. That's what you call a shark. Now we'll sing the Baby Shark song. All right, so that's a short. What happens is the electricity found a shortcut. And so it does not go around the light bulb, which would not be on. It found a short way to go around. And what happens if I have a short? Well, usually what happens is the power is going to come around and go through that little short. It's going to bypass the load, and all these wires are going to get very melty. They will get hot. And there's a little secret that all of this really works off of magic smoke. Have you heard that theory? So I told you about electrons and all that, but it really runs on magic smoke. And if you do that, you let the magic smoke out, and then it quits working. Oh, stupid, but all right. So that's a short. There's open and a short. If I had to take my pick between what I wanted, if I had to have an error, would I rather have an open or a short? Much rather have an open, because a short it can create a fire. Now that's why we have circuit breakers installed. Circuit breakers and fuses, so it's too much current draw and it'll pop the circuit breaker. But that's another lecture for another time. All right, so we have all of that going on. And what color am I at? Black. All right, that brings us up to call number 2, Ohm's Law. Or what some of you may want to call it, simply just Ohm's suggestion. Now, I'm going to tell you that it's a law, but often in class and in lab, I will ask you, oh, so what is this now, just Ohm's suggestion? Because you'll have some weirdness going on, and I'll be like, well, no, that's Ohm's law pretty much said it doesn't work that way. It has to work in accordance with the law. So we will talk about said law. And just because it's in my notes, we might as well just do it again. So Ohm's law, we have units of electricity. And what are those units that we discussed? I will write, we had 3 of them.
Amps, current, resistance, and
Photons?
No? Go ahead, Mike. Michael, yeah. What do you got?
Ohms.
Ohms. Okay, so what was ohms? What were we actually measuring? Resistance.
And then no
Resistance, which was represented by the letter R.
and then I for electricity.
No, not I for electricity.
I for current.
Current. Okay, current.
And V for
E
Current, which was the letter I, and what?
E for voltage.
Voltage. Voltage with the big letter E for resistance, intensity, and electromotive force, if you will. I'm going to add one more of them now. And that is a watt.
What?
A what? I was hoping somebody did that. A watt. And what letter should I give watts?
P.
W. Well, who said P? P is good. W or a P. All right, named after James Watt. And let's see. We'll get into the formulas here. So a watt. B, let's see. Ohm's law. Well, let's say formulas. Formulas. All right, so Ohm's law. Well, I don't even know if I want to write this one. I'll say it and then I'll write something different. Ohm's law is, and I quote, the current in an, oh, we should write it. The current in an electrical circuit is directly proportional to the EMF. We should probably stop right there before we finish this sentence and talk about what that means. The current, that is the flow of electricity, is directly proportional. It means it goes up at the same rate as the EMF goes up. So if EMF goes up, current goes up. What is EMF? Electromotive force, which is also called Voltage, that's the E right there, V. So if the voltage goes up, what happens to the current? It goes up. All right. This wasn't so hard, was it? We'll put this right. Voltage, V-O-L-T-A-G-E, just to make sure we're all on the same page. And inversely proportional to resistance. So inversely proportional to resistance. So what happens if the resistance goes up? It goes down. That's the inverse. This is proportional. This is the inverse. So a proportional, they go up together. Inverse goes the other way. So if resistance goes up, current's going to go down. Another way of saying Ohm's law is 1 volt causes 1 amp of current to flow through 1 ohm. How you like that? Beautiful, right? Yes?
So back in the current and electrical circuit is proportional. So basically, if the voltage goes up, the current goes up.
That is correct.
Okay, and then, so if there's more resistance, the current will go down.
Yes.
Because there's more.
Yes. Now, when it comes to Ohm's law, there are lots and lots of actual formulas. These are the actual formulas. So we have I, which is what? Current. So it's E divided by R, or P divided by E, or the square root of P divided by R. Resistance, which is E divided by I. You can see how it goes. And then we have E over here, which is voltage, and power over here. So you got to memorize all of these, right? No, I wouldn't want to do that. So here's what I memorize. All right. So the ohms, you will see that when I work on any type of electrical thing, I just write this. EIR. And if I can look at that and then remember that I like pi, which is not hard for me to remember how much I like pi, I can do it all. Because I like pi. There you go. There's my pi. So power equals I times E. So that's a whole other thing. But up here, I have, all you have to do is cover up one item and it tells you what it is. So if I want to know what E is, all I got to cover up E and it's going to tell me I times R. If I want to know what I is, it's E divided by R. See how that works? So if I had to write it out, E equals I times R. So cover up the E goes I times R. I equals E divided by R, and R equals E divided by I. Everything you need to know is right there. And just remember how much I like pi. But who doesn't like pie, right? You like pie? You like cake? Now I want pie. What? Okay, remember watts is the same as power, all right? So, because it, I mean, who wants to put W equals IE? I got nothing for you there.
Yeah, there's no pi there.
There's no pi there, so I don't like that, but it's the same thing. All right? Everybody with me so far on this?
Yes.
All right, let's talk a little bit about power. What the heck is power? You know what? I don't think we need to learn that for this class. We'll just back off. We'll talk about it later. It's all based on watts and power, and then you get the horsepower based on an English workhorse, and we'll cover that. All right, so we talked about the dangers of electricity yesterday. I don't think we need to write it down. You'll figure that out, right? All right, so we got this requirements. All right, so everybody's ready to move on? We got all this, right? Everything's down because we're going to build right upon it. Now, if I take a simple circuit, let's not take a simple circuit. Let's talk about formulas. So simple circuit. Now I'm going to put a bunch of resistors in here. All right, I got my resistors, I got a path, I got a current. When you are doing, we're going to solve for stuff like this. I prefer that you do E, I, R, and then in the next class, I'm always going to want P. So I'm at E, I, R, P, E, I, R, P, and move it a little bit. E, I, R, and P. And if you could do it in that order, it makes my life a little bit easier. And so if I call this one resistor 1, that's R sub 1, resistor 2, resistor 3, this is a battery, but this does not represent the battery necessarily. It's the total. It's total voltage, total current, total resistance, and the total power used up by the circuit. And so this becomes E of 1, E of I, 1, 1, 2, 2, 2, 2, and 3, 3, 3, 3. And if I assign a value for each one of these resistors, I'm just going to make up something. We'll say 25 ohms, and we'll put 30 ohms and 15 ohms. I need to know the total amount of resistance for this circuit. Now, our total, this is the formula, to figure out the resistance for this circuit, like I need more room, R total equals the resistance of resistor 1 plus the resistance of 2 plus the resistance of 3, so on and so on. So you simply just add the resistances, whatever you see together. And this is for a series circuit. Tomorrow, the next day, we're going to talk about parallel circuits, and everything's different. Very different. So you cannot use these formulas for a parallel. This is a series. Series means what?
In line.
How many paths?
One.
One path. Parallel means there's at least 2. All right. So resistance. If I want to know how to calculate E total, it is the voltage drop of 1 plus the voltage drop of 2 plus the voltage drop of 3. If I want to know I total equals the current through 1, which equals the current through 2, which equals the current through 3, so on and so on. And what I'm saying when I tell you this is that, number one, to figure out the resistance, all I have to do is add up the resistance. So it's 25 plus 30 plus 15, which is? 70. Thank you. 70 ohms. And if I assign a voltage, now I'm just going to say 12 volts, just because I just picked it out of my head. I can look at that and say, why, that's 12 volts. Where did 12 volts come from? Right. Where did the number 12 come from then? That's right. I made it up. Came out of my head. I just assigned it. It could have been any number I wanted, but I chose that. All right? In 1 minute, somebody's going to say, where'd 12 come from? All right. So using the formula E, I, and R, I can solve for I, can't I? So yes, because I can. Because here's the deal. Anytime you know 2 of 3 things, you can always solve for something. Can I solve for E right here?
No.
How about I here?
No.
Nope. E, I, nope. Yes, question.
Can we have a formula sheet?
Can you remember EIR? Yeah, well then you don't need one. So the short answer is that, or short answer is no. Nope, you got to remember EIR. All right, so I want to know now, what is the total current in this circuit? Did I move too fast for anybody? What's my total current? You should have a calculator out. It should be helping along. I want to know I, so I cover up I, and it is E divided by R. So it's 12 divided by
70.
equals
0.1714.
Okay, so 0.17, we'll say 1 amps. How many milliamps is that?
171.
Well, 171 milliamps. All right, we'll just put that over here because I don't have a lot of room. Well, look at that. Now, if I know that, can I solve anything over here? Well, I want you to remember this up here. Even though my screen is getting a little crowded. I total equals what? All right, which means that whatever it is here, that current only has one path to flow. So current leaves the battery, and we'll go conventional right now. Current leaves the battery, current flows through this. Guess what? The same current that flew through that was flowing through this also has to flow through this. And the same current also has to flow through this. That is why the current is the same through the whole circuit, because whatever current went through here, how many paths does it have to get back? One, so it's got to follow that around. So everything stays the same. 171 amps, 0.171, 0.171 amps, 0.171 amps. Now, I told you over here that the voltage total, which is 12, is equal to the voltage drop across 1, 2, and 3. What that means is every time it's going to lose some voltage through every one of these resistors. Every one is going to rob a little voltage. But if I measure the voltage across each one, which is to say that I actually put the ohm meter across the resistor, positive and negative, I will measure, there's a difference of potential because it's different from this side than it is from that side. So if there's a difference of potential, the meter's always going to read something. So it's also called the drop. Now mathematically, I can figure out the drop. How can I figure out the drop across E1? I times R is correct. So it's 25 times 0.171. And the voltage drop would be 4.275 volts. Which is to say that if I put a voltmeter from here to here, it would read 4.275.
Can you go over that again, please? How you got the 4.275?
Okay, where did I get 4.275? How far back do I have to rewind?
Like the last thing.
That's what you did, I times R.
Okay, it is I times R. Mathematically gives me 4.275 volts. What does that mean? That means that if I put a voltmeter across that resistor, it will actually read 4.275 volts. That is a difference of potential from one side of it to the other. Huh? Mathematically, you can't get it?
I mean, I did I times R.
0.171 times 25.
He's doing it at the first resistor.
Let's do it again, but we'll do it over here now. What is the voltage drop across resistor 2? .171 times 30. So what do you get? 5 point what? 5.13 what? Volts. All right. How about down here? .565 volts. All right, this is really the essence of what you're going to be doing a lot of in this last project and in a lot of the electricity class. Now, other than the fact we haven't done power yet, in this class I asked for EI and R. Are we finished? We've got EIR, 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 and EIR. Are we finished?
No.
Why are we not finished?
Just solve everything now.
Well, I said we're not going to do P. We could do P, but have I filled out all the blocks?
Yeah.
What block did I not fill out? What? E total's 12. It's right there.
You know, it's complete.
I total's right there, 171. Anything else? Got that. I got that. Everything's there.
Yeah.
All right. Here's where you should never walk away from it. There's one last check you can do. We have not done this check.
Yeah.
E total equals 1 plus 2 plus 3. So even though it's all there, I'm going to double check myself. 4.275 plus 5.13 plus 2.565 equals, what do you guys get? Comes out to be 11.997. Does that mean I made a mistake?
No.
Just rounding errors. It's not a big deal. So yeah, it's close enough to 12. So do you see how to solve for something like this?
So we will be given a given for at least one of the, at least E, I, or R. We will be given.
I'm just going to give you a couple resistors and say you guess what I was thinking. Yes, of course. Yeah.
So is there ever going to be an instance where they don't give you E total, but they give you E1, 2, and 3?
I am they, and yes.
Okay.
Yeah. Oh, there's instances where I'm not so much in this class, but yeah, in the next one, I'll make it as hard as I can. But even as hard as I can, it's still very simple. It just does not get so hard. There's always.
So many things that
So the
you
current
can do
will be
differently.
every on each resistor the same.
Yes. So let's look at some takeaways before we go on break here. Unless you want to go on break while I talk, that's okay too. Just be quiet. So a couple of takeaways on this. One, the current flow is always the same through here. So if I didn't give you I total, but I gave you the current flow through number 3, what's I total?
Same.
Same. You know, that's kind of how it's going to go. I'll do something like that, and then you go, oh, it's the same, right? And resistance, you just add up the resistors. It's very simple to add them. Very different in a, don't try and do this with a parallel circuit, it won't work. And voltage is just divided up. So we go across here, we lose 4.2 volts. Go across here, we lose 5 volts. Go across here, we lose 2. Go across here, and it's going to read the same as across there, 12. All right, let's do break, 10 minutes.